Even American engineers, the people who built the Golden Gate and the Brooklyn Bridge, looked at the blueprints for this thing and said it could not be done in this ocean, over this seabed, in this amount of time. China built it anyway, and in a few minutes, you are going to understand exactly why nothing like it exists anywhere else on the planet.
Before we go further, drop a comment right now. Where in the world are you watching from, and what time is it there? Hit subscribe if you are new here. This is where the world's most extraordinary stories come alive. Now let's begin.
To understand why this crossing is considered one of the hardest engineering problems ever solved, you have to understand the stretch of water it crosses. The Pearl River Delta is one of the busiest, most dangerous, and most economically important bodies of water on the planet. It connects three of the world's most important cities: Hong Kong, Macau, and the mainland city of Zhuhai. And for decades, the distance between them was measured not in kilometers, but in hours. A container truck moving cargo from Zhuhai to Hong Kong had two choices: drive nearly 4 hours around the entire delta on congested mainland roads, or load the cargo onto a ferry and hope the weather held. There was no direct route, not because nobody wanted one, because nobody believed one was possible. The distance to cross is roughly 55 kilometers of open water, more than 34 miles. Longer than the entire length of Manhattan repeated over 20 times in a row. For comparison, the Golden Gate Bridge, the bridge most Americans picture when they think of a great bridge, is less than 3 kilometers long. This crossing needed to be almost 20 times that length, over open sea, not a calm bay. And the water itself was hostile. This part of the South China Sea sits directly in the path of some of the most violent typhoons on Earth. Wind speeds during a direct typhoon strike can exceed 250 kilometers per hour. The seabed beneath the water is soft marine clay in some sections, capable of swallowing a badly designed foundation over time. And running straight through the middle of the crossing zone is one of the busiest shipping lanes on the planet. Hundreds of massive cargo vessels, some carrying over 20,000 containers, passing through every single day. Any bridge built across this water would have to be tall enough to let those ships pass beneath it. But the shipping lane also happened to sit directly beneath the approach path for Hong Kong International Airport, one of the busiest airports in Asia. A bridge tall enough for ships would be too tall for planes on final approach. This is the exact kind of problem where most countries would simply say the crossing is impossible and leave it as a ferry route forever. China's engineers looked at the same problem and designed something almost nobody outside the country believed could work. A bridge that becomes a tunnel in the middle of the ocean, without a single visible seam where one method fails and the other begins. The bridge that turns into a tunnel. Here is the part that made engineers in the West stop and stare at the plans twice. For most of its length, the crossing is a bridge, 6 lanes wide, resting on massive concrete piers driven deep into the seabed. But as it approaches the busiest section of the shipping lane, the bridge does something almost no infrastructure project in history had attempted at this scale. It sinks. The roadway descends onto 2 artificial islands built specifically for this purpose. And between those 2 islands, it disappears entirely underwater, becoming a 6.7-kilometer undersea tunnel, over 4 miles of roadway sitting on the ocean floor, deep enough that the largest container ships in the world can pass directly overhead with room to spare. Think about what that actually requires. You are not digging a tunnel through solid rock, the way engineers usually do. You are assembling it, piece by piece, on the seabed itself. In a stretch of ocean known for violent storms and shifting currents. The tunnel was built using 33 individual concrete segments, called immersed tube sections. Each one roughly 180 meters long and weighing around 80,000 tons. Heavier than the Eiffel Tower. Repeated 33 times, sunk one after another into position on the ocean floor, with a margin of error smaller than the width of a human hand. Each of these segments had to be built on land, floated out to the exact coordinates, sunk with millimeter precision, and sealed against 33 neighboring segments so that not one drop of seawater could ever find its way inside. If even one of these seals failed at depth, the consequences would not just be an engineering failure. They would be a catastrophe, with the 6-lane highway sitting directly beneath the ocean. American engineers who reviewed early details of the project openly questioned whether this level of precision was achievable at this scale, in open ocean conditions, using a construction timeline this aggressive. The immersed tunnel techniques that existed before this project had never been attempted at this length, this depth, or in waters this exposed to typhoons.
Towering waves batter the massive artificial islands, locked into the center of the typhoon corridor.
China's engineers didn't just prove it could be done. They finished the tunnel with a level of sealing accuracy that surprised international engineering observers.
It is absolutely zero.
Reporting a project so precise that not a single one of the 33 segments needed significant rework after installation. An outcome many experienced tunnel engineers considered close to unbelievable for a project of this scale. Building islands that didn't exist.
New land where once there was only water. This is the future of infrastructure.
Before the tunnel could exist, the two islands that anchor it had to exist first, and neither of them was there. Engineers needed solid ground in the middle of open ocean. In water up to 44 meters deep in some sections, on a seabed made of soft marine mud that could not support a foundation the traditional way. Traditional land reclamation, the process of slowly dumping rock and sand until an island rises out of the water, would have taken years, and in this location, the timeline simply did not allow for it. So the engineering team designed something that had never been used at this scale anywhere in the world. Enormous hollow steel cylinders, some as tall as a 20-story building, driven directly into the seabed like giant drinking straws pushed into wet sand. 120 of these steel cylinders were sunk into position, forming a solid ring. Once locked into place, the space inside was filled, creating a stable, artificial landmass capable of supporting roads, tunnels, and buildings. Built in roughly 1 year, a process that conventional reclamation methods would have taken several times longer to achieve. This technique, called the large diameter steel cylinder method, had never been attempted at this depth or this scale in the world before this project. It was designed specifically because nothing that already existed could solve the problem fast enough or strong enough for what this crossing demanded. Designed to survive the end of the world. Every part of this crossing was designed around a single number, 120 years. That is how long the structure is engineered to last. More than double the design life of most major bridges built anywhere else on Earth, including in the United States, where the average major bridge is designed for a lifespan closer to 50 to 75 years. To hit that number in this specific location, engineers had to design for the absolute worst-case version of nature. The bridge and tunnel system is rated to withstand an earthquake measuring 8 on the moment magnitude scale. Strong enough to be counted among the most powerful earthquakes ever recorded on the planet. It is rated to withstand a super typhoon with sustained winds, strong enough to be classified at the very top of the tropical cyclone scale. A storm intensity that would shut down entire cities and ground every flight in the region. And in a detail that stunned engineers when it was first published, the bridge's piers were designed to survive a direct collision from a 300,000-ton cargo vessel traveling at full speed, roughly the weight of the largest oil tankers on Earth, without the structure collapsing. For comparison, most Western bridges are engineered around a maximum design vessel far smaller than that, because a collision from a fully loaded supertanker is considered such an extreme, unlikely event that most bridge designs anywhere else in the world don't plan for it at all. In the Pearl River Delta, with hundreds of massive ships passing daily, engineers treated it as a scenario they had to design for, not around. The human scale behind the steel. Numbers. This large are difficult to hold in your head, so here's what the finished project actually required. More than 400,000 tons of steel went into the bridge sections alone. Enough steel, by some engineering estimates, to construct more than 60 replicas of the Eiffel Tower. Over 1 million cubic meters of concrete were poured across the piers, islands, and tunnel segments combined. Enough to fill hundreds of Olympic-sized swimming pools. Roughly 9 years passed between the start of major construction and the crossing's opening. With tens of thousands of engineers, welders, divers, and laborers involved across the full length of the project at its peak. And underwater, specialized diving teams performed thousands of individual dives to inspect, align, and seal the immersed tunnel segments by hand. At depths where visibility can drop to almost nothing and currents can shift without warning. A category of construction work that ranks among the most physically demanding engineering labor performed anywhere in the world. Why the West builds different, not better. It's worth pausing here, because this is where the comparison usually gets misunderstood. The United States has incredible bridges. The Golden Gate remains one of the most recognizable structures on Earth. The Chesapeake Bay Bridge Tunnel, completed in Virginia in 1964, was actually the first crossing in the world to combine a bridge and a tunnel system in a similar way. And for decades, it was considered one of the most ambitious engineering feats in American history. But scale changes everything. The Chesapeake crossing runs a little over 28 kilometers. This Chinese crossing runs 55 kilometers, almost double the length, through far more hostile ocean conditions, using tunnel immersion techniques refined decades after the Chesapeake was built. Aimed at surviving typhoon and earthquake conditions the Chesapeake was never designed for. The honest comparison isn't that China did it better than the engineers who came before. It's that China took a technique the world already understood in a limited form and pushed it further than anyone had ever attempted. At a length, depth, and hazard level nobody had previously combined into a single structure. That is the part that consistently catches Western engineers off guard. It isn't that the idea was new. It's that nobody else had been willing or able to build it at this scale in this amount of time, in water this dangerous. What it actually changed. Before this crossing existed, moving goods between Zhuhai and Hong Kong by road meant a trip of close to 4 hours around the delta. After it opened, that same trip dropped to under 30 minutes. For a region responsible for a staggering share of global manufacturing and shipping output, cutting a 4-hour trip down to 30 minutes isn't just a convenience. It restructures how an entire economic region functions. Factories in Zhuhai gained faster access to Hong Kong's port and airport. Logistics companies redesigned entire supply chains around the new travel time. What used to be 3 separate economic zones, functionally isolated by water, began operating as one connected region. this is the part that rarely makes it into the headlines about the world's longest sea crossing. The engineering is what gets people's attention. The economic transformation is what actually justified spending years and enormous resources building it. The part even critics couldn't argue with. No mega project this size is without controversy, and it's worth being direct about that instead of pretending otherwise. The project faced real criticism during construction. Concerns about worker safety incidents, cost overruns beyond original budgets, and questions from environmental groups about the crossing's impact on the local population of Chinese white dolphins living in the delta. Engineering teams responded by adjusting construction methods. And timelines in an attempt to reduce disruption to the dolphin population, including altering piling schedules and installing monitoring systems. Though environmental groups continued to debate how effective those measures actually were. What even the harshest critics of the project's cost and process did not dispute was the underlying engineering achievement itself. When international structural engineering bodies reviewed the completed crossing, the tunnel and island construction techniques were recognized as genuine advances in immersed tunnel engineering. Methods now being studied by engineers in other countries, planning their own extreme sea crossings. That's the detail that tends to surprise Western viewers most. This wasn't just China building something big. It was China solving an engineering problem that had stopped other countries from attempting a similar crossing anywhere else in the world at this scale. How it stacks up against the world's other giants. To really understand what this crossing achieved, it helps to line it up against the other legendary bridges people already know. Japan's Akashi Kaikyo Bridge, connecting Kobe to Awaji Island, held the record for the longest suspension bridge span in the world for decades, and remains one of the most respected engineering achievements in Asia. It stretches just under 4 kilometers. This Chinese crossing runs 55 kilometers, roughly 14 times longer, though it uses a completely different combination of bridge, island, and tunnel engineering rather than a single suspension span. Denmark's Great Belt Fixed Link, connecting 2 of the country's main islands, was considered one of the most ambitious sea crossings in Europe when it opened in the late 1990s. Combining a suspension bridge and an undersea tunnel across roughly 18 kilometers of water. It was, for years, one of the closest things in the Western world to what this Chinese crossing eventually became, except at roughly a third of the total length and without the same earthquake and super typhoon design requirements. Even the Øresund Bridge, the striking bridge tunnel connecting Denmark and Sweden, that most people recognize from film and television, spans just under 16 kilometers total. It is a genuinely elegant piece of engineering. It is also less than a third the length of the crossing you are watching a documentary about right now. None of this is about declaring a winner. Every one of these projects solved a real problem for the country that built it, under real constraints with the technology available at the time. But when American and European engineering commentators reacted to the completed scale of this Chinese project, the consistent reaction wasn't disbelief that China could build a bridge. It was disbelief that anyone had found a way to combine every one of these separate engineering challenges. Suspension levels span distances, immersed tunnel technology, artificial island construction, and extreme disaster resistance requirements into a single 55-kilometer structure, on a construction timeline measured in years rather than decades. The people who never saw daylight. The engineering numbers tend to dominate the conversation, but underwater construction on this scale comes down, ultimately, to human beings doing extraordinarily dangerous work far from any camera. The specialized diving teams responsible for guiding each of the 33 tunnel segments into place worked in conditions most people would find almost unimaginable. Visibility at the required depth could drop to near zero due to sediment stirred up by current. Divers worked with precision instruments to guide segments, weighing tens of thousands of tons into alignment with tolerances smaller than a few centimeters, fully aware that a miscalculation at that scale wasn't a minor error. It was a project-ending failure. Engineers on the surface described the sealing of each tunnel joint as one of the most tense phases of the entire 9-year build. Every one of the 33 seals had to hold under enormous water pressure indefinitely for the structure to be considered safe for public use. There was no way to fully test a seal except to complete it and monitor it under real conditions. This is the part of mega-project engineering that rarely gets highlighted in the headlines about world's longest or world's biggest. Somewhere beneath the surface of the South China Sea, ordinary construction workers and engineers spent years solving a problem that had never been solved at this depth or this scale anywhere on the planet, and very few of them will ever be publicly recognized for it. Section 11. Standing at the midpoint. Picture standing on one of the artificial islands at the exact point where the bridge disappears into the tunnel. Behind you, 6 lanes of traffic stretch back toward the mainland, elevated high enough above the water that a typhoon could be raging beneath you and you would still be safely above the worst of it. In front of you, the road simply vanishes into the ocean. No ramp warning you. No sign announcing it. The highway just goes under and stays under for more than 6.5 kilometers, while some of the largest ships ever built pass silently overhead. There is nowhere else on the planet where you can stand in that exact spot and feel both of those realities at once. A bridge built to survive an earthquake capable of leveling cities, and a tunnel built to let you disappear beneath a typhoon, while it destroys everything on the surface above you. Somewhere off the coast of southern China, there is still a road that does not end where the land ends. It survived 9 years of construction. "120 steel cylinders sunk into the seabed, 33 tunnel segments sealed by hand at the bottom of the ocean, and a design standard built to outlast almost every other bridge on Earth. And it is still out there right now, carrying traffic across 55 kilometers of open water, disappearing beneath the waves exactly where the largest ships in the world need to pass. Proof that the hardest engineering problems on the planet aren't actually impossible. They're just waiting for someone willing to build the answer.